Hi, good morning. This lecture will be on limit superior and limit inferior. And because of I'm using Zoom pre-account, the meeting may be restricted to only 40 minutes. But I hope within about two such sessions, we may be able to complete whatever we wanted to know about LimSup LimInf. Okay. So without much ado, let's get into the job. Okay. So the best reference for this will be a book of mine written along with Ajit Kumar, a basic course in real analysis. Okay, so let us start with the definition. So I am given a sequence xn. I am given a sequence xn of real numbers, and I assume this is a bounded sequence, bounded real sequence. Okay, let us also assume that for all n, mod xn is less than or equal to m. That means xn's lie in the interval minus m2 plus m. Okay. Now, given such a bounded sequence, we want to construct two sequences, monotone sequences. Okay, let us look at how to do that. Let us look at Tn. Okay, this is by definition LUB or supremum of xn, xn plus 1, and so on, which is the same as supremum of this set xk, where k is less than or equal to n. Okay, so let us call this set as an. So what does an consist of? It consists of terms of the sequence xk, where k is greater than or equal to n, right? Okay. Before we go further, let us look at, make an observation. What's the relation between Tn and Tn plus 1? The answer follows if I observe what is the relation between an and an plus 1. See, an starts from xn plus 1 onwards, whereas an plus 1 starts from xn plus 1, xn plus 2 onwards. Therefore, an plus 1 is a subset of an. Therefore, we know that whenever A is a subset of B, then we know supremum of A is less than or equal to supremum of B. Therefore, supremum of an plus 1 will be less than or equal to supremum of an. But what is supremum of an plus 1? That is Tn plus 1. And this is Tn. Therefore, we see that the sequence Tn is increasing. But before even doing this, I forgot to say why Tn exists. Why Tn exists? Notice that xk's are less than or equal to m. Therefore, the set an is bounded above by m. Therefore, this is a non-empty bounded subset of R, and hence the supremum or LUB exists. Okay, right. So we have defined Tn, and we have found that Tn is an increasing sequence. Very good. Now I want to define Sn. Can somebody say what it should be? Look at, I have the set an. I define Tn to be the LUB. And why it exists? Because ANs are bounded above by M. Just think for a second, then you know what Sn should be. What should it be? ANs are bounded below by minus M. Therefore, the infimum or the GLB also exists. So let us define it. Okay. Therefore, let us define infimum Sn to be infimum of ANs. This, that is GLB or infimum of Tk, where k is greater than or equal to n. right? Now look at Sn and Tn. What's the relation between them? Sn is the infimum of An, whereas Tn is the supremum of An. Again, we know if A is a non-empty subset of real numbers for which infimum supremum exists, then infimum of An will be less than or equal to infimum of supremum. In fact, we don't require infimum or supremum. We need only lower bound and upper bound. Why? Because let's look at Xn. This is an element of An. Now, what's the relation between Sn and Tn? Sn is less than or equal to Xn because Xn is an element of An. Yeah? And Xn is an element of An. Therefore, what's the relation between Xn and Tn? That's less than or equal to Tn. Therefore, as a corollary, we see that for all n, Sn is less than or equal to Tn. Okay. Now we want to observe the pattern of Sn. It's a sequence. Now notice that in Tn, we saw it's an increasing sequence. Okay. So I invite you to make a guess. What do you think the nature of the sequence Sn would be? Let's look at. Okay. Again, it depends upon the same answer. Suppose A is a subset of B, assume non-empty. So what's the relation between infimum of A and infimum of B? Right? Any lower bound for B will also be a lower bound for A. Right? And hence, the greatest lower bound of B will be a lower bound for A, and hence the GLB of B will be less than or equal to GLB of A. In other words, infimum of A is greater than or equal to infimum of B. So this tells us Sn, which is the infimum of An, should be greater than or equal to infimum of An plus 1. Sorry. Yeah, right. Right? This is which is Sn plus 1. Therefore, what have I found? I'm sorry, I retract this statement. Now, so we know that An plus 1 is a subset of An. Therefore, infimum of An plus 1 must be greater than or equal to infimum of An. But infimum of An by definition is Sn plus 1, that's greater than or equal to Sn. That means the sequence Sn is increasing. Is it okay? So, given a sequence Xn, we have defined two sequences Sn, which is increasing, and another sequence Tn, which is decreasing. Okay, and Sn is less than or equal to Tn. And notice that minus m is less than or equal to Sn, less than or equal to Tn, less than or equal to capital M. Because for this, m is an upper bound, therefore it's a supremum, namely Tn will be less than or equal to m. This is true for all n. Okay. So these are the facts we have done. Now let's look at some easy examples. Try to understand the concepts. The first sequence is the easiest one. It's always good to start with this, the alternating sequence Xn. Now what is An? Depending upon the parity, either it will start with the 1, minus 1, etc. repeated, or it may start with minus 1, 1. If n is odd, it will start with 1. If n is even, then it will start with minus 1. Therefore, what do I see? The supremum of An is 1. The infimum of An is minus 1. Therefore, Sn and Tn are constant sequences. constant sequence minus 1 and Tn is a constant sequence plus 1. Do you agree with that? Okay. Let us look at one more example. Okay, you can look at few more examples in my book, but let us look at one more example. And suppose I define xn to be uh, n by 5 minus the integral part of n by 5. Okay, for each year, right? So what do you want? You want to look at what are Sn's and Tn's. Okay, this may be a little abstract example, but it's very easy. What does it mean? Let us look at n by 5. Okay, so what we can do is by division algorithm, n I can write 5 times m plus r. R will be less than or equal to 0 less than 5. Do you understand that? Therefore, r takes values only in the set 0, 1 up to 4. Is that clear? Therefore, n by 5 will be what? It will be 5m plus r by 5. That means m plus r by 5. You understand? And this fractional part, sorry, integral part, this is the integral part. Integral part of this, that is going to be m, right? N by 5 divided, then whatever is the greatest integer less than or equal to that number. That is same as saying m, right? So this will be m plus r by 5, but minus m, therefore this will be r by 5. Let us call Rn, where Rn is this thing. You understand this? Therefore, Rn at for any n takes values between 0, 1 by 5, and etc. up to 4 by 5. Do you understand? Therefore, what should be my Tn? Tn is going to be supremum of An. Supremum of An consists of Rn, Rn plus 1, etc. But this thing, number Rn, Rn plus 1 takes values only here, and certainly I can find some number, something, 4 by 5 form. Therefore, supremum is 4 by 5, and infimum Sn is going to be 0. Therefore, we have seen Tn is again a constant sequence 4 by 5, and Sn is constant sequence 0. Okay, now let's do the third example. This is slightly abstract. Okay, and with this we'll stop the lecture. So let us assume Xn is a sequence, convergent sequence in R. So let us assume Xn converges to X. Okay, now I want to find out something about Sn and Tn. Is that okay? Right. So let's look at, since Xn is a convergent sequence, converges to S, you give me any epsilon positive, I know there is a natural number n, so that for all k greater than or equal to n, xk lies between x minus epsilon in the interval x minus epsilon to x plus epsilon. Yeah, very good. Therefore, we are not going to find in this case Sn and Tn, but we will find bounds for Sn and Tn. Okay, so let us look at what is Tn. So let us assume my n is greater than or equal to capital N. Then I want to find a bound for Tn for n greater than or equal to capital N. What is Tn? Tn is going to be supremum of xn, xn plus 1 onwards. And what is n? This little n is greater than or equal to capital N. Therefore, that xn lies here, right? Therefore, each of the xn here is bounded above by x plus epsilon. Therefore, this is less than or equal to x plus epsilon. Do you understand that? Right. Now, for similarly, we have a Sn which is equal to infimum of xn, etc. Each of the xn is lies in this interval if n is greater than or equal to capital N. Therefore, xn is greater than x minus epsilon. Therefore, x minus epsilon is a lower bound for an, and Sn is the infimum, greatest lower bound for an. Therefore, this must be greater than or equal to x minus epsilon. So, what have we arrived at? We are arrived at given an epsilon, choose a capital N with this property. Then, for each n greater than or equal to capital N, we have shown that x minus epsilon is less than or equal to Sn. Of course, Sn is less than or equal to Tn, but that's less than or equal to x plus epsilon. Okay, we have not found out Tn and Sn, but you have a very good estimate using the nature of the sequence, namely its convergence. Okay, we will put it to use within a minute. Now let's go back to the abstract thing. So Xn is any bounded sequence, bounded real sequence, again with contained in the interval minus m2 plus m, etc. It goes without saying. Then we have defined Tn, a sequence which is decreasing, and Sn, a sequence which is increasing. And we also found minus m less than or equal to Sn less than or equal to Tn, which is less than or equal to m. Now notice that Tn is a decreasing sequence bounded below by minus m, therefore it must be convergent, right? Tn is a bounded decreasing sequence. But decreasing sequence bounded below if you want to be recall your theorem. Therefore, it must be convergent. Where does it converge? We know that Tn converges to the infimum of Tn's. This is a set. You remember that? This is not the terms of, you form the set consisting of terms of the sequence. Okay. We call this as T. We call T as the infimum. Why does it exist? Each of the Tn's are bounded below by minus m, therefore. Okay. Therefore, what do I know? Tn's are decreasing. Tn is a decreasing sequence bounded below by minus m. Therefore, I know it converges. I also know where it converges. Where does it converge to? It converges to the infimum of the terms. Okay, infimum of Tn. So this exists and call it T. This T is called lim sup of the sequence Xn. Okay, is it clear? Good. Now, for similar reason, let us look at Sn. This is an increasing sequence, but bounded above by capital M. Therefore, I know again Sn converges to some S. What is that S? That S is nothing other than supremum of Sns. Okay, if I increase sequence bounded above, we know that it converges to the supremum of the terms. Therefore, this. Okay, this S is called LimInf of the sequence Xn. We will also write LimInf of Xn. Okay, right. Now, what's the relation between S and T? Let's look at that. We know that Sn is less than or equal to Tn for all n. Now, what do I know about Sn and S? Sn is less than or equal to S, right? And what do I know about Tn and T? Remember, T is the lim in. This is the infimum of Tn. Therefore, what do I know about this? T is less than or equal to Tn, right? Now, is that clear? S is less than or equal to T. Yeah. Why? Let us look at. Uh, you understand what I am trying to say? Right. If this is a very general case, right? If I'm using a very general fact. Let me just recall what we are using. If an is less than or equal to bn for all n, and if an converges to a and bn converges to b, then I want to claim a is less than or equal to b. That is very easy because bn minus an is greater than or equal to 0. And by algebra convergence sequence, I know it converges to b minus a. Therefore, b minus a must be greater than or equal to 0. So you get this result, right? So I know Sn converges to S and Tn converges to T, but Sn is less than or equal to Tn. Therefore, I know S is less than or equal to T. In particular, we have seen that lim of the sequence Xn is always less than or equal to lim_sup of the sequence Xn. Okay, take a time, pause your video, go through it once again. After 30 seconds, restart the video and go to the next point. So let us go back to our examples. In the case of minus 1 to the power n, then we know lim_in is minus 1, lim_sup is plus 1, because Sn is a constant sequence minus 1, Tn is a constant sequence minus 2. And in the case of n by 5 minus n by 5, okay, we know lim_in is 0 and lim_sup is 4 by 5, right? Now let's look at the convergence sequence. Let us assume Xn converges to X. Okay. Now let's go back. If we give me an epsilon positive, we had already seen something which is happening. Let's recall. Okay. For n greater than or equal to capital N, I know X minus epsilon will be less than or equal to little sn, less than or equal to Tn, that is less than X plus epsilon. Right. In particular, for capital N, this must be true result. Right. So call it 1. So from 1, equation 1, what do we get? Given epsilon positive, there is a n such that x minus epsilon is less than or equal to Sn, which is less than or equal to Tn, which is less than or equal to T for every n greater than or equal to n. In particular, x minus epsilon is less than or equal to Sn. And that is less than or equal to Tn. Are you intrigued why I have given so much gap? You'll see in a minute. Right? Now, what's the relation between Sn and little sn? Sorry, what is the relation between Sn and S, the lim_in? Remember, lim_in is the supremum, yes, is the supremum of Sn. Therefore, Sn is less than or equal to S, right? But I know what is the relation between S and T. S is less than or equal to T. Now, I also know what is the relation between T and Tn, because T is the infimum or the greatest lower bound, in particular, lower bound for all my Tn's. Therefore, this T must be less than or equal to T capital N, that's less than. That's less than or equal to, sorry, this is what happens when I get carried over. In the class, somebody would have pointed out x plus epsilon. Yeah, very good. So, what do you think I would have done? So I have x minus epsilon and x plus epsilon and s and t. Therefore, what does this say? So in particular, this epsilon. Therefore, t minus s, which is greater than or equal to 0, that's less than or equal to x plus epsilon, because t is less than this, and s is greater than that. Therefore, minus s is less than minus of that, minus x minus epsilon, which is 2 epsilon. Therefore, for any epsilon given, I have shown t minus s is less than 2 epsilon. That Therefore, this says by Archimedean property t minus s is 0, or lim n lim sup of xn equal to LimInf of xn. Both are equal, right? The next question I can ask is, do I know what they are? So what you have shown is they are lim sup equal to lim, but do I know what they are? Right? Okay. So let us look at it. We will prove in a minute what it is. Okay. So let us go to the next page. Let this, let it be there. So what I have shown now? I have shown that if xn is a convergent sequence, then lim equal to lim sup. I claim now we want to claim lim n of xn. I know which is equal to lim sup of xn, and I want to claim it is nothing other than x. Yeah. So how do you prove that? That follows very easily, because look at that. X also belongs to this interval. X has to be somewhere here, right? Therefore, S and T are equal now. They are the same point. So you collapse them. Okay. Therefore, what I have? I have x minus epsilon and x plus epsilon, and the midpoint is x, and my S and T is equal to T lies somewhere here. Call it T. It lies here. Therefore, what's the distance between x minus T? That will be again less than or equal to epsilon. And remember, x and t are constant, and their distance is less than or equal to epsilon. Epsilon is arbitrary. That means x minus t equal to 0. Therefore, what you have shown is, if xn is convergent, then lim sup of xn equal to x, convergent to x, then lim inf of xn. In other words, let us write it, which looks little better. Lim sup of xn equal to limit of xn equal to lim inf of xn, right? So in the convergence sequence, we have found out lim sup, lim inf are equal, and the same proof also shows they are equal to the limit of the sequence. Okay. Thank you very much. Now go through the proof video again and look at each point. Please stop, pause it for a while, review, make sure that you understand before you go to the next step. Okay. So you should try to internalize this thing. It's not mere understanding will not help. Okay. Thank you very much for listening. Have a good day.